Welcome back to Logic, Language and Information. In this lesson we get to see predicate prologue in action. Begin with a review of last lesson. Program clauses are either single facts or conditional rules built from star atoms, which contain variables as well as names with predicates as well as identity and difference. The automated reasoning task in Prolog is to determine whether or not the existentially quantified goal formula is a logical consequence of the universally quantified program clauses. Okay, first, the syntax used in Prolog writes program clauses conditionals in reverse order, with the consequent coming first. The consequent is referred to as the head of the clause. It is followed by the symbol :dash, read as if, and referred to as the neck of the clause. And then finally the body of the clause, which is the list of star atoms in the antecedent conjunction, with the AND connective indicated by a comma. The reverse order will make more sense when we see how Prolog works in lesson 6.4. It is the head of a program clause that has to be consulted first when processing a Prolog query. Now, Prolog has a bunch of syntactic idiosyncrasies. We will first go through quite a few examples of program clauses and queries, and then later give a summary list of the syntax and other stuff that we've been using in basic predicate Prolog. Now, our running example of a knowledge base will be family relationships between characters in the internationally popular series of books and TV shows called Game of Thrones. We start with the main line of the Stark family, with the data structured using the predicate parent AB, meaning child A has parent B. The parent predicate is a popular one in Prolog introductions, but be careful which order of arguments is being used. Now, the character Ned Stark, who dies at the start of the first series, has parent Rickard Stark, who in turn has parent Edward Stark. Going down the generations, there is Robb, Sansa, Arya, Bran and Nickon, who have as parents Ned Stark and Catelyn Tully. Then there's another character called Jon Snow, who also has Ned Stark as parent. Notice that program clauses always end in a full stop. All of these facts can be written using real atomic formulas with names and no variables, as shown. To keep to one character names for the predicate logic formulas, we have used the second letter of their name for Robb, letter O, and for Rickon, letter I. Now, we also include in our knowledge base some facts about being male or female using one-place predicates and the corresponding atomic formulas of predicate logic. Now, logic consequence requires that the goal be true in all models in which the logic program is true. From the list of atomic facts given so far, we can describe a model with 10 objects corresponding to the 10 names that occur in the atomic facts. The parent atomic facts tell us that the interpretation I of P for the two-place predicate P must have ones in the table as shown, but we do not yet know anything about the other entries in the table. Likewise, the columns for the interpretations of the M and F predicates show the one entries corresponding to each of the atomic facts about being male or female, but on the basis of the program clauses so far, we do not yet know anything about any of the other entries in the table. One of the intuitions with Prolog is that by computing logical consequences of a logic program, one learns more about the models of the program by possibly filling out more ones. So next we consider conditional program clauses, still with names and not yet with variables. For example, the mother of Robb Stark is Catelyn Tully if a parent of Rob Stark is Caitlin Tully, and Caitlin Tully is female. And here's the corresponding logic formula, using capital O for the predicate for mother because capital M is already used for is male. When this program clause is added to the previous list of atomic facts, we can draw the logical consequence that the mother of Rob Stark is Caitlin Tully. Using the analogous construction for the father predicate, we can draw the logical consequence that the father of Rob Stark is Ned Stark. Clearly, this pattern of mother of, if, parent of, and female is just one instance of a generalisation that applies to all people. Likewise, for the pattern father of, if, parent of, and male. So this is where universally quantified program clauses come into play. In PROLOG, variables are marked by starting with a capital letter. This program clause says that for all ways of instantiating the variables x and y, the mother of x is y if a parent of x is y and y is female. And here is the corresponding universally quantified logic formula for this program clause. Next, for all ways of instantiating the variables x and y, the father of x is y if a parent of x is y and y is male, and the corresponding logic formula. Next, we can take a step up in complexity. X is a sibling of y if there exists a z such that a parent of x is z and a parent of y is z and x is different from y. So this is our first case of an extra variable in the antecedent of the conditional that is read as existential when it's within the scope of the conditional antecedent. After prenexing and being pulled outwards to the scope of the whole conditional, it would become universally quantified. So the corresponding program clause formula is for all x, for all y, for all z, if x is a parent, x has z as a parent and y has z as a parent and x is not equal to y, then x and y are siblings. Now, some more program clauses with variables. X has grandparent y if there are two parent relationships. There exists a z such that x has z as a parent and z has y as a parent. Clauses for grandmother and grandfather add in extra conditions of being female or being male. Now, an important feature of PROLOG is the ease of writing recursive program clauses. Intuitively, x has ancestor y if x has parent y, or if x has parent z and then z has parent y, or there are 3 generations, or there are 4 generations, or so on, leading from x back to y. Written recursively, x has ancestor y if x has parent y, or if x has parent z and z has ancestor y. This captures the feature that ancestors are inherited down the generations. Here it is important to put first the base case of the one generation link, and the second recursive clause will unwind in stages. First the 2 generation links, then the 3 generation links, and so on. Without care, it is rather too easy to accidentally send PROLOG into an infinite loop. The recursive pattern as used here in the ancestor predicate is the most basic way of defining a recursive two-place predicate. So we can combine all of our example program clauses into one logic program, which we've given the name Game of Thrones-0.pl, where the .pl part is the file extension for PROLOG programs. But the file itself is just plain text. The file lists the program clauses for general family relationships, all using variables understood as universally quantified, followed by a list of parent predicate facts, and then the male and female predicate facts. Now, before seeing a bunch of example queries to this logic program, yielding some of its logical consequences, we pause first to consider the models which make true all the program clause formulas for this logic program. The smallest such model has 10 objects in the domain, using the one-character standard names as shown corresponding to the 10 name persons in the logic program. So we can see, going back to the logic program clauses, that there will be no additional atomic facts generated by the program about the parent male or female predicates. We can see this because those three predicates do not appear anywhere in the head of any of the conditional program clauses. All the clauses that are there are all about new predicates like mother, father, ancestor, and so on. By taking instances of these universally quantified program clauses, we can learn new facts about these new predicates, but they will not yield any new facts about the parent male or female predicates. Now, so back to our partial model of the Game of Thrones-0 logic program. If we think about completing all the blank entries according to whether or not the corresponding fact is a logical consequence of the program, we see that for this logic program, all those blank entries will become zeros. In the theory of logic program, this is what is called the Hebron model of the logic program. For a simple example of a program whose Hebron model will see extra ones appear in the blank entries, consider one expressing facts about adjacency of objects of the form A is adjacent to B, together with universally quantified clauses expressing that adjacency is a symmetric predicate. Then the logical consequences of the program will include the reverse order fact saying B is adjacent to A, giving extra ones in the Hebron model. Now, we now have a real live PROLOG program. Let's use it with an implementation of PROLOG and start asking some queries. Now, we use LLI2, a free open source implementation that has been developed at the University of Amsterdam. There are versions for Microsoft Windows, Macs, and for Linux and its variants. You are encouraged to install a version of PROLOG on your local computer if you can and start exploring it yourself. The .pl PROLOG files we've mentioned are all available for download. So start up the SWI PROLOG software and then load in the program file Game of Thrones-0.pl. There are 10 universally quantified clauses expressing family relationship predicates, 13 parent facts and 10 male-female facts to give a total of 33 clauses. Let's start with an atomic query. Are Jon Snow and Sansa Stark siblings? The query goal is entered after the query prompt, signified by $dash. And queries, like program clauses, end in full stops. We hit the return key on the keyboard and get the answer true. To get back to another query prompt, we can hit the return key again and we are ready for another query. How about we ask, are Robb Stark and Rickard Stark siblings? Try that one, and false. No, Rickard is the grandfather. It is Rickon who is siblings with Robb. When the answer is negative, PROLOG returns straight away to the next query prompt. Okay, does Rob Stark have Rickard Stark as a grandparent? Well, yes. When the answer is positive, PROLOG waits for further user response, either the return key or the semicolon key, with the semicolon being a way of asking, is there any more, or are there any more answers? Now here, there is no further answers indicated by false, because true is the only answer for this atomic query with no variables. The semicolon input is really only of use when the query has variables that need to be instantiated. Now, variables are marked in PROLOG by starting with a capital letter. We can ask which youthful people have Rickard Stark as their grandparent. Oops, here we go. Remember, we are asking PROLOG to give us the names of such young people, not just true or false answer to the question of whether or not the existentially quantified goal formula is a logical consequence. So, we get our first answer of Jon Snow, and then using the semicolon, we can ask for more such names. Another is Rob Stark, another semicolon to ask for more. We get Sansa Stark, another semicolon. Arya Stark, I think you say that, another semicolon, Bran Stark, another semicolon, the young one, Rickon Stark, keep going, another semicolon, and finally, PROLOG says no more. That's it for existential witnesses for this youth variable. When you use a PROLOG implementation yourself, you will notice that the semicolon is not actually printed on the screen. We're including it here to make clear what is being entered from the keyboard. Okay, how about a query with two variables? We want to list all the youth-elder pairs where the youth has the elder as their grandparent. Well, the first answer has youth as Ned Stark and elder as Edwyle. PROLOG finds this pair first because the parent and male facts needed to establish this are at or near the top in listing order within the logic program. Put in a semicolon to ask for more, and we get the pair Jon Snow and Rickard Stark. Another semicolon to ask for more, and continuing. And finally, we do get a false, saying from PROLOG, there are no more answers. Okay, so one way to ask if Jon Snow and Arya Stark have a parent in common is this, where the syntax here, P1 equals sign P2, means P1 and P2 can be unified by instantiating the same name. The query answer is yes, witnessed by Ned Stark, but there are no more witnesses for P1 equals P2. Okay, let's see the recursive predicate ancestor at work. Ask the question, who is an ancestor of Bran Stark? Well, first answer is his father, Ned Stark, and then his mother, Catelyn Tully, then his grandfather, Rickard Stark, and then great-grandfather, Edwyle. And finally we get false because there are no more witnesses for this query. Because of the way the recursive ancestor predicate was constructed in the two program clauses, the recursive unwinding starts with the nearest ancestor and proceeds backwards through the generations. Okay, so to compare, let's run that query again, but this time after the first answer for A as Ned Stark, we instead just hit the return key instead of the semicolon. In this case, PROLOG just goes back to the query prompt straight away, interpreting this as meaning that the user is happy to stop after this many witnesses. Okay, so there is no data about the parents of Catelyn Tully, so a query asking for her ancestors returns with false. And for a simple example of a query using identity, there's this one, does Bran Stark have an ancestor A called Edwyle Stark? And the answer, not surprisingly, comes back Yes, A is Edward Stark. And this is the only answer. Okay, now it's your turn. Which of the following PROLOG program clauses correctly express that X and Y are cousins? Now note that cousins share a grandparent but not a parent. So take your time reading the different options and noting their sometimes quite subtle differences. Okay, how did you go? The only one that does the job is B, which says that X and Y are cousins if there are W, Z and V such that X has parent W and W has parent Z, Y has parent V, V has the same parent Z, Z is the grandparent, X and Y are different, and W and V are different. Without the extra clause saying W and V are different, we would get siblings rather than cousins. Now, if you have any comments and questions, then as usual, go first to the course notes and then to the discussion boards. Okay, so the cousins predicate won't be much fun with the data in our first example logic program, but created a larger logic program called Game of Thrones 1-1, which is available for download, which has a bunch more Game of Thrones family relationship data, as well as a few more family relationship predicates. It includes data for the Lannister family of characters, as well as a bit more of the Stark family tree. We'll now make a list summarising the basic PROLOG features we have been and will be using to form a mini user manual. First, conditional program clauses are written in reverse order. The B is called the head of the program clause, the colon dash is the neck, and the antecedent list A1, A2 up to AM is the body of the program clause. The procedural meaning of a conditional program clause is we can establish an instance of the head B if we can establish appropriate instances of all of A1, A2 up to AM in the body. In contrast, facts are purely declarative with no body or neck, just a head. All program clauses, conditional rules or facts must end in a full stop. PROLOG distinguishes syntactic categories based on the character strings used as identifiers. All names and predicates must be identified by a character string starting with a lowercase letter, distinguishing them from variables whose identifier must start with an uppercase letter. The first letter is the signifier. The rest of the character strings can be made up of any combination of lowercase, uppercase letters, digits, and the underscore character. To express the difference star atom, X is not identical to Y in PROLOG notation, use the cannot be unified symbol, which is \= To express the identity positive star atom X is identical to Y in PROLOG syntax, we will be using the can be unified symbol, which is just the =. It is the same symbol that PROLOG uses when returning existential witnesses for goals with variables. Now, a word of warning, there are several different notions of identity or equality that can be used in PROLOG, with the differences between them only apparent when working with functions, complex terms and arithmetic operations. You may see things like double equals or equals \= equals and others. In the basic PROLOG without function symbols that we are using, terms are only names or variables. So the pair of difference and identity relations that we have picked will work for our purposes. Okay, back to our user manual. We use the semicolon key on the keyboard to ask PROLOG if there is more than one existential witness for each of the variables in the goal of the query. While we have shown the semicolons as appearing on the screen in our example PROLOG sessions, this is to remind us of what key to press. Well, at least in the SWI PROLOG implementation, they are not printed to screen. This capacity for requesting more witnesses means that PROLOG is non-deterministic in the sense that queries can have 0, 1, 2 or more answers. A PROLOG program P is written as a list of program clauses, each ending with a full stop, and saved in a plain text file with a file extension .pl. So we think of a logic program as a knowledge base of information about some subject domain. Now, the order of star atoms within a clause and the order of program clauses within a program will turn out to matter for how PROLOG executes, which will become clear in the next lesson. PROLOG uses the pool of names occurring in a logic program and the goal when taking instances of universally quantified program clauses, as well as universally quantified negated goals. The substitution method for assigning names to variables is called unification in PROLOG. We will see it at work in the next lesson. Because of the way unification works, there is actually a requirement to use identifiers for variables in the goal that are completely different from the identifiers for variables used in the logic program. Predicates of arity 1 or more must have parentheses separating the predicate name from the terms, the names or variables occurring as arguments, with commas between the arguments. Predicates are distinguished by their identifier together with their arity. So, for example, we can reuse the identifier cousins and also have a 3-place predicate that holds between X, Y and Z if X and Y are cousins and Z is their common grandparent. Okay, so in summary, a logic program P is a list of program clauses with variables understood as universally quantified, whilst a goal G is a list of star atoms with the variables understood as existentially quantified. The automated reasoning task is to determine whether or not the existentially quantified goal formula is a logical consequence of the universally quantified program clauses. To get PROLOG to answer such a logical consequence question, you load up the program file into your PROLOG software, enter the goal star atoms in a list after the query prompt, end the list with a full stop and press the return key, and then PROLOG will either answer positively by giving existential witnesses for the variables in G, or it can answer simply true or false, or these are not the only options, there is no answer at all because it gets stuck in a loop and crashes. So, like the proof tree method we saw in the core part of the course, the proof tree method used by PROLOG is a refutation procedure. So in effect, PROLOG supposes that all the clauses in P are true, but the goal G is false, and then tries to derive a contradiction. Unlike the proof tree method, there will only be one inference rule called resolution. So how PROLOG answers queries is the topic of the next and last lesson in this series. So see you next time.